try to stay in this area. Try to
Yeah.
stay. All good?
Yeah.
Okay. Okay, good afternoon, everyone. So, today's lecture is sort of not our usual lecture, but rather we'll go through a tutorial on Verilog hardware design language, and then sort of a show and tell / walk you through the process of taking a design and mapping it to an FPGA board, partly as a as preparation for the optional design assignment. So Salma, who hopefully half the class should know, that's your TA, she's going to talk about Verilog. She has worked in this area prior to coming to UCLA when she used to work for one of the EDA companies called Mentor Graphics. So she kind of design chips and stuff like that. So she'll go over Verilog. And then Paul Martin, who is soon to be Dr. Martin, he is, as you might gather, a senior PhD student, and he enjoys working with hardware, software, and also he was a TA for this course last year. But anyway, he helped pull together this whole design assignment and kind of the whole tool chain and stuff like that around it. So he'll kind of both, like I said, do a show and tell of like what's involved, but also the specific tools and all that we are going to be using. So roughly speaking, I don't know, Salma, you'll take what, 45 minutes, an hour, or something like that? Or, yeah. So the first half of the class would be Salma's, and then Paul probably around half an hour, 40 minutes. So, since we have some hardware and all, so one of the things that Paul has sort of arranged is there's a little camera out here so that you get to see what is happening on the board up on the screen. But feel free to sort of come and sort of talk with him and all towards the end of the presentation as well. So without wasting more time, I'll let
Okay. Okay, hello everyone. So today we'll start an introduction on Verilog. So what you have been taken in the class this quarter is you design the hardware using gates, right? What if we have a language that can describe these gates and actually tell you, no, you need a mux, you need an and, you need an or, so you don't need to actually define the logic yourself. No, you say what you want and leave the how to a tool to do it for you. Okay, so this is why we need the hardware description language, the HDL, and there are different language for it. One that you're going to take today is the Verilog. So it's widely used in the design of digital integrated circuit, and it's used in different stages in designing the IC, the integrated circuit. First, in designing the hardware itself, simulating it, making sure that it works correctly, making sure that the timing analysis is correct like you took last class, and also to make sure that when you download what you have designed or what you have wrote into the hardware, okay, it works correctly. It works as you want, okay? So it's not new. The language has been going back till to 1980s, so it has been there for a while. So this is the design flow when you design Verilog or when you design hardware description language. At the beginning, you system analyze and partitioning, like what we did. We have the data path, we have the control path, we have the part that do the logic, the combinational logic. So at the beginning, when you look at what you want to do, you partition it. You want this part to be the control, you want this part to be the data path, and so on. Oh, okay. Okay, thank you. Okay, sorry about that. So this is the design flow for Verilog. At the beginning, as we said, that you partition your design into parts, okay? And then you write the Verilog code for it. We will see how you can going to do that. And then write test cases for what you have wrote to make sure that it works correctly. Then you make simulation, okay? What is simulation? It's a word that you're going to hear a lot in the hardware design. It means that you verify the functionality of what you wrote, okay? Does it work as you want or not? Does the timing constraints works or not, okay? Is there a timing violation or not. This is at the beginning, okay? After you write your Verilog code and make test cases, you simulate it. That's the meaning of simulation. And then when you make sure that everything works as you want in the simulation stage, you go to something called synthesis. Synthesis is a tool that is used in order to transfer what you have wrote to actual gates, to ANDs or muxes and so on, okay? And different boards have different allowable gates. Not all boards supports all gates, okay? So that's why the synthesis tool requires to have what is the architecture, what is the board that you want to synthesize your gates on. Some boards doesn't have muxes, for example. Some boards doesn't have decoders, okay? So you have to provide the architecture of the board so that the synthesize tool can map what you have wrote to the gates that are allowable on this board. Then the next step, after you do the synthesis, the synthesis tool will generate something called a netlist. The netlist is just a textual description of the gates that will describe your logic, okay? So it's something that looks like this. It's a text that says, okay, you have ANDs, you have ORs, you have inverters, you have wires that connect the ANDs to the ORs, and so on, okay? So the output is an actual text that describes this logic. Then there are something called simulate at gate level, but you are not going to go through how you do simulation at the gate level. But in general, in practice, it's common to spend like 70 to 80% of the design cycle just writing the Verilog and testing it and making sure that it works correctly, and only 20 to 30% in the verification of the gate, in the simulation of the gates, okay? Then the last step is actually make the device, program the hardware. There are two types. One is called the FPGA, which Paul will show you, and the other one is called ASIC. ASIC is application specific. Once you fire or deploy your design on your ASIC, it's targeting just a certain or a specific application. The FPGA, think of it as a breadboard, okay? It's something that you can deploy different designs on it as if it's a prototype, okay? You are deploying different design, you are testing it, and it's usually used for small applications in general, okay? So this is the design flow, and we will try to talk about each part of it in this talk. Yeah, so at the beginning, when you write your Verilog code, you will hear something called RTL design, register transfer level. So it's not just writing Verilog code. No, you have to write a Verilog code that can be synthesizable, that can actually be transferred to gates to be deployed on the hardware, okay? The RTL design is like the register transfer level. It's like what you have taken in the design of the FSM. You have registers, you have combinational logic, and actually the signal is transferred from the combinational logic to register, to combinational logic to register, and so on, okay? So you transfer your values through registers, okay? So that's why it's called RTL. So remember this, that you have a Verilog and you want to synthesize it to actually be deployed on an IC, into an actual hardware. Okay, so how do you write a good synthesizable Verilog? That's what we are going to try to do. It's not sufficient that the Verilog is working correctly, but it has to be synthesizable. It has to work on the hardware that you want to deploy your design on. So let's start with a simple design. Suppose that you want to design this very simple logic circuit, AND or invert, okay? You have 4 inputs, A, B, C, D, and you make OR between A, B, and C, D, and then, and then you made OR invert to get the F, okay? So Verilog use concept of modules, okay? A module, you can think of it as has 2 parts. You define the ports, the inputs and the outputs, and you define the body, what actually this module is going to do. So there are 2 parts in the module, okay? The port declaration, which represents the external interface to the module, which are A, B, C, D, and F, okay? And the module body represents the internal description of the module, its behavior. So you have here 2 ANDs and 1 OR invert, or NOR, okay? So how can we do that in Verilog? So if you look into this snippet of the code, you will see at the beginning a comment when you write any code, you have a comment. So the comment is like the C and the Java. It has 2 slashes, and you write your comment. And the module starts between 2 keywords in Verilog, module and end module, okay? Between the module and end module, you write the behavior or the description of what this module should do. So if you look at the first line, which is the module name and the ports, the AOI is the name that you give to the module. It's your choice. It's not a keyword in Verilog or not anything. It's just what you want to choose as a name for this module. So we choose it as AOI and or invert, okay? And then between parentheses, you will find the description of the ports. You have input A, B, C, D, and output F, okay? And then you define the behavior. We will go through that now, but then you end your module using end module, okay? So the module name is arbitrary, and it's your choice. And module and modules are Verilog keywords. And you must make sure that all the inputs and the outputs are defined in the module description. So you say, I have A, B, C, D as input, and I have F as an output. You should define that, okay? And the ordering is not very important, but it's usually we define the inputs before the outputs, okay? Let's look now, we have taken care of the interface, the module, in module, and the ports. Now let's look at the functionality. What do we want this module to do, okay? So we say that we want to do A and B, and we want to do C and D. We are going to OR them together and invert, right? So this line is actually what we have seen. We are going to AND A and B together, C and D together, take the OR between them, and then invert, okay? So this is called the module body. We assign is a keyword. We assign F, which we have declared in the module description as an output. We assign this value to this description, okay? So when you write a line like this in Verilog, what happens actually is whenever any value in these ports or in these signals change, the value of F will change. It's not that all of them should change at the same time for F to change. No. Any one of them changes, F will change. Okay, that's the difference, okay, between hardware and software. And you know the symbols of OR and NOT and AND, so you can apply them as well in the Verilog code. And that's it. That's all we need to define the AND or invert gate in Verilog. We define the modules, we define the ports, we define the behavior, and that's it. We finished the Verilog code for AND or invert code, AND or invert design. Now, what we have described is a very simple logic, right? Sometimes it's not that simple. Sometimes it's more complex. Okay, so that's why with the ports, we need something called wires. Wires is an actually electric connection. It representation of an electric connection. So if we look at the same design that we have implemented, we can look that there is a wire between the and this OR, right? And there is another electric connection between this AND, which is CD, and the OR, right? So we can define these electric connections explicitly by saying that we have wire connecting the and the OR, and we have another wire called O connecting the OR and the invert, okay? So that's why sometimes we need the wire, and the wire is used in the connection between the different modules. So let's see for the same design, how can we put wires in it? So what you see is what you implement. What you visualize is what you implement, okay? So you see what? You see you have wire AB, you have wire CD, and you have wire called O, okay? And you assign the values for these wires. So if you look here, you say assign AB equal A and B. So I have the wire that's called AB will have the value that is going to compute it from A and B. And you have another wire called CD, assign it to C and D, okay? Another wire called O, assign it to AB or CD, whatever the values that come on this wire and the value that come on CD wire, OR them together. This is going to be the assignment for wire called O. And then assign the invert of the value on wire O to the output F. Okay? We wrote this for assignment in one line before, okay? But suppose that you want to explicitly assign value to a wire in your design, that's how you're going to do it. And this will do exactly like what we did, okay? Each line of these will be executed whenever any value, whether in A, B, or C, D, or A, B, or C, D, or O changes, this line will be executed, okay? They don't have to be executed in sequence. No, they can be executed concurrently. Whenever any value of these changes, the assigning of this line will change as well. Now, there are different ways to assign the wires. In the previous one, which is the first block, we used what? We define the wire. We're saying we have 3 wires, and then we used the assign keyword, assign A, B, for example, equal A and B. You can do another way to do it, another syntax in Verilog called wire assignment directly, okay? You say wire AB, while you define the wire, you put the assignment directly. So you don't have to write the keyword assign. You just say wire AB equal A and B. So these are 2 different ways to assign the values to the wires. And there are no advantage or disadvantage to these 2 ways of writing the wires. They are both the same. It's just for your convenience, whatever is convenient for you to write in the syntax. Okay? Now what we have seen is just what? It's just 1 bit, right? We have A, B, C, D, and all of them computed to 1 bit. You can actually define in Verilog multibit. Okay, like you wrote in your course. This is the same way. Okay, you have the brackets. You define the width from 31 to 0. So you have a wire that carries 32 bits. Okay, and it's called a bus. If you have a wire that carries more than 1 bit, it's called a bus. Now we have defined one module which makes AND or invert. What if I want to use this module as a block into another design? Okay, what if I, like what you have taken, for example, you designed the decoder using ANDs and OR, and you use the decoder as a block in other design. Okay, what if you want to do that? So there is the design hierarchy. You define different modules, and then you connect them together. So you have here the AND or invert module in this square, and you want to make this connection to it. Okay, you want to have 2 inverters, and you have different inputs to it, and you want to design this hierarchy. So let's call this square, this whole design 1. You have AND or invert, the one that we have just designed, and pair of inverters. Okay, so you have something called module instance. You design different modules and you create instance from them and connect them together. Okay, so yes.
Was there ones on cell phone nearby or no? You didn't see any?
I didn't see.
Okay, let's research to.
Yeah, I'm sorry. Yeah. Okay, so let me directly go to this one. So we have, if you look at module definition, you have 2 module definitions, right? You have module AOI, which we have just implemented, that do the AND, 2 ANDs, OR, and invert. And you have another module definition, which makes the invert of the input, assign F equal invert of A. This is like the second line in the code. Okay, so you see 2 module definitions, one for the invert, right? And one for the AND or invert. And you want to create this design hierarchy at the top. So what you do is you create instance from the module that you have defined and connect them together. So you create 2 inverter called G1 and G3, the one that have green line underneath. So invert G1 and invert G3, okay? And you create an instance from the AND or invert module, AOI G2. Okay, and then you connect them together. We will see how we are going to connect them together. So this is called the module instance. You create different definition for it's modularized. You create different modules, okay? You partition them, and then you connect them together using module instances. So there are different ways to connect the modules with each other, okay? One of them is called module port connection and the position mapping, and the other called named mapping. Position mapping is just when you define the module instance. Remember, any module is defined by what? Inputs, outputs, right? At the beginning of the definition of the module, you say input A, B, C, D, output is F, right? So when you make position mapping, meaning that at the position of the A, I'm going to put the wire that's going to connect the other design to the input A. So for example, you have here what? AOI G2, select B, A, select B, FB. The 1, 2, 3, 4, the 4 lines from the end, okay, from the bottom. When you see the definition of the AOI, you see what? Input A, B, C, D, output F. So the position mapping is you look at what you want to map in the input to what you want to map in the actual design, in the full design. So look at the beginning, look at the figure. You want to connect what? You want to connect A with wire called what? Select B. So at the position of A, in the definition of the module, I'm going to write what? Select B. Can you see what I'm saying? Now let's look at what in the definition of module AOI, you see input A and then B. So the next one that you're going to put in the module instance is what you're going to connect to the input, naming B. And that's in the figure, we have B is connected to an input from outside called A. Okay, so you see what? Select B, comma, A. Can you see what I'm saying? Let's see the other one, C. So C, in the definition of AOI, is the third one. And it's connected in our figure, in our top design, with a wire called select. So in the third argument, I'm going to put select. This is called position mapping. At the position, I'm putting the wire that I want to connect to this instance of the model. Okay? Now let's see the other one, for example, invert G1. So G1, which is the first invert, the first degree invert, the input to it is what? The input to it is A, and the output from it is F. So, but in my definition, in my top design, the input for it is A, and the output from it is select B. So I'm putting it in the position map. Okay? The other one, now this will be very confusing if you have a lot of inputs and a lot of outputs in the definition of your module. Okay? You have to make sure that you put what you want in the right position. Okay? Sometimes it will be confusing. So there is another way called what? Called named mapping. You put, this is like the third one, the third line from down. Okay? This is a way of defining the connection of the module instance using named mapping. And instead of putting what you want in the right position, no, you say the port that's called A in the definition of the module, I'm going to connect it to FB. Okay? The one that is called F in my definition of the module, I'm going to connect it to F. Okay? So this is another way in creating the module instance. Instead of putting it in the right position, no, you make something called named mapping. This one is better so that you don't make mistakes in the connection of the module, so you make sure that you are connecting the right ports with the right wires when you are connecting different modules with each other. So actually, I prefer the second one, which is the named mapping, so that we don't make mistakes. Okay? Let's dissect the code. Okay, so what I have just been saying is what is here is that we have ports that are defined in our module interface, and we map it to the wires in our top design. Okay, any question on this so far? Any question? Anything that's not clear, ask me. If you don't understand something, ask me. Feel free to interrupt me at any point. Yes. this one. Yeah, I skipped this part. Okay, so sometimes, look at this one. Sometimes you define the wire explicitly, like what we did. We say we have a wire called AB, we have a wire called CD. Sometimes Verilog lets you make the definition of the wire implicitly if it's only 1 bit. Okay, if the width of the wire is only 1 bit, you can actually put, if you look at the 3 lines that are marked with green here, okay, I didn't put a definition for select B as wire. Okay, but when you create the module instance, you say, okay, I'm connecting select B with select B from G1 and G2. Implicitly, the Verilog will know that this wire is connected to this wire. You don't have to explicitly define it. But that only happens for 1 bit width. Okay.
What value does select B have?
Which one?
Select B, what value does it have?
At the beginning, select B is don't care. At the beginning of the start of the simulation, everything is don't care. Okay. If it will confuse, you can of course define the wires. Okay, but that's like a thing that Verilog lets you do. Okay. I actually skip it so that I don't confuse you. But yeah, thank you for asking. Any other question? Everyone understand how to make a module, how to create instance, what are ports, how to create design hierarchy, how to connect modules with each other? Everything is clear? Okay. So yeah, so we finished writing a small Verilog design. Let's write a test for it. Does what we want actually implement what we desire or not? Okay, so we write tests for what we have designed. This is called test benches. So test benches in hardware design consist of 2 parts: the stimulus and the response. The stimulus is test vectors, meaning that assume that A has this value and this value and this value, like the A, B, C, D of the input. Suppose that the pattern of the input is 1, 0, 1, 0. Okay, I want the output to be this value. Does actually the output give what I want or not? Okay, so you define test vector, you define patterns for the input and patterns for, or the golden output of the output, and see does actually what you see from the output is what you want or there is a mistake. Okay, so it helps you in the design stage to make sure that what you have designed is actually correct. Okay, so remember, the test bench is not intended to be downloaded on the hardware. No, what is intended to be downloaded on the hardware is the design. Test benches is just to test your design. It's not intended to be downloaded on the hardware. So that's why sometimes you can do things in the test bench that you can't do in the actual design. Okay, you can define things, you can do functions, you can do other things in the test benches that cannot be done in the actual design, because actual design need to be synthesized on the gates on the FPGA. Test bench, no, test bench is just for you to make sure that it works correctly. Okay, so let's create a test bench for the design that we have just implemented. So as we said, test bench consists of 2 parts: stimulus and response. Stimulus is the input pattern. You define some inputs and you check the response, you check the output. Does the output match what you want or not? Okay, and there are a lot of engineering in defining the inputs that will cover everything. Suppose you have a very big design, it has a lot of input patterns. Are you going to test for each different input, or some input pattern, and it will give you a significant result? Okay, so actually this part is important. How are you going to define the input pattern, and how are you going to see the response? So in the syntax of Verilog, how you write the test bench, now this is different than the design. This is a test bench. So you define a module, you name it anything. So I name it design 1 test, for a test for the design 1 that we have just designed. It doesn't have any ports. Okay, in the test bench you define a module, it doesn't have any ports. And you have initial. Initial is a key word in the Verilog. It's the start of your test bench. and you create an instance of the module that you want to test. Remember the module instance? So I'm creating an instance called M from a module called design1. Okay? And it has select, it has A, it has B, and it has F. And then the other part is the analysis. I'm going to check the output and make sure that it matches what I want. So these are the two parts in writing the test bench. So the initial keyword is used to start my simulation. This is the beginning of my simulation. Okay? So let's see. This is the initial block in our test bench. So it's a stimulus. The meaning of stimulus is that you enforce values for the inputs and see does it match the output or not in the analysis. So in the stimulus, you say initial, and inside it, it has begin and end. Between begin and end, you put the patterns of the inputs that you want to test. So I have what? I have select, I have A, I have B, and I have F, right? So inside it, I have select A, B, and F is the output. So inside it, I say at the beginning, I put select equals 0, A equals 0, B equals 0. It's testing, okay? So you are forcing values. And then you see hash 10. It means after 10 time units, I'm going to put A equal to 1. Then after 10 time units again, select equal 1. Then after 10 time unit, B equal to 1. So as if you are creating a wave, okay, values. After 10 units, put A equal 1. Another 10 units, put select equal 1. And see how the values are going to change. So it's time units, meaning what? It's not 10 seconds, it's not 10 nanoseconds, it's time units. And the unit is actually defined in the simulation tool. So you have a tool that you write your test bench on it, and it lets you say whether the time unit corresponds to 1 nanosecond or the time unit corresponds to 1 second or what. You define this. So remember, it's not 10 seconds. It's not 10 nanoseconds. It's 10 unit time. And you define the unit time in your tool. Okay? So what we have wrote here is actually this diagram. Right? At the beginning, you put select A, B equals 0. Look at the timeline and see. At the beginning, at 0, select A, B were equal to 0. And then after 10 time unit, I put A equal 1. So you see A becomes 1 after 10. And then another 10 unit, you see select become 1. Another 10 unit, you see B equal to 1. So what we have just written is that we created this. We created the values of these signals. Now let's look at the response. So we created the stimulus. We created these inputs. So the inputs to our design had this shape of waves, had these values. Okay? Now let's look at the result. Will it actually match what we want or not? So you write another block called the analysis block. And it's the same. Initial, begin, end. And inside it, you monitor the values of F, which is the output of our design. So it's very easy to actually monitor the response in Verilog because it has a keyword called monitor. Okay? So you see in this snippet, it's a syntax in Verilog, $monitor. So monitor is a keyword in Verilog that allows you to see how the values are changing. Okay? So you are saying monitor with time the values of select, the values of A, the values of B, and the output F. Okay? And you can put whatever string pattern that you want. Okay? Look at it as if it's like printf or print in C and Java. Monitor is something like this, and you are printing to the screen these values. Okay? And as you see a comma space, as if when you are printing, you have a space between the time and the values. Okay? It's like the printing in the C and Java. So you are monitoring this value. If you look at the right box, you see what? At time 0, A, B, C, select A, B, F, all have zeros. Okay? So you see it's printing what? 0 and then 4 zeros. At time 0, select A, B, and F all have values zeros. And then at time 10, select was 0, and remember we say what after 10 time unit, I'm raising A from 0 to 1. So you see that A becomes 1. You see what I'm saying? Okay, the second line in the block, 10, after 10 time unit, A has become 1. So it become what? 0, selected 0, A has become 1, B I didn't change. Will the output be 1 or not? Now the output of F is 1. This is like the last bit, F is 1. Do I actually expect to have a 1 or not? This is the analysis. You are seeing the output. Does it match the input pattern that you have defined or not? Okay, you are testing your design. Does the output match what you want or not? Okay? So you have a keyword called monitor and another keyword called time. Time is just taking the time from your simulation tool. Okay, so that's why you say you just print $time and it prints for you 0, 10, 20, 30, and so on. Okay? Any question on this so far? Yes.
There was one code saying end of comments block / star. It was in the previous.
This one? This one?
No, it was saying end of comments block / star.
In the test benches?
No, it was before. One of the slides.
This one?
No.
Okay. So do you remember the question? What was it?
No, the code was saying end of comments block / star.
You mean this? End of module description, end of comment? No? Okay, then maybe come after. What? Which one? Multi-line comment, which one? Ah, you mean like a /$ asterisk? Ah, okay. So I don't know where this is in the code, but he was asking, so when you put comments in your, okay, so best practice, when you write the code of Verilog or when you write any code in general, try to put comments, okay? Try to put what this line actually means. This is for you, okay? So when you write comments, it's 2 slashes and you write the comment. You write what you want. When you compile your code, whatever is after these 2 slashes is not taken in the code. It's just for you, okay? So it's 2 slashes and you write the comment. Sometimes if you want to write like different lines of comments, like multiple lines, there's another way to do it. So you write /*, put all your lines, and then */. Okay, you can come afterwards and I can show you that. But just you can write slashes and your comments. Okay. Okay. So again, we are still in the test benches. Okay, we write the stimulus, we write the response, and we see the output. Now, the initial makes the running only once. Initial, begin, end. It execute only once. Sometimes in your design and in your test bench, you need to execute something always. You want it to run always, okay, forever. You want this hardware to keep on running forever, okay? So you write this in something called always block, okay? So always is like initial. It's a block. You started with always, begin, end. And inside it, you write all the code or all the behavior that you wanted to keep on executing forever. But you can't have something called forever, right? You have to have something control over it. How you are going to control it. So in the always block, there's something called sensitivity list. It means execute this block whenever between these brackets changes. Whenever any signal between this bracket changes, this block will run. So it's called, this block is sensitive over the sensitivity list. Okay? So for the same design, suppose I want to have the AND or invert design to keep on running forever. Whenever any values of the input change, execute it. Whenever any input changes, execute it. So you need to have an always block. always block at A or B or C or D. Look at the box, the second box. So you are defining the sensitivity list over this behavior. When will this behavior execute? It will always execute whenever any value in the sensitivity list changes. Okay? So this block is called sensitive over the sensitivity list. And you put into your sensitivity list the signals that you want to be sensitive over. Now make sure that when you write combinational logic, you have to make sure that whatever the behavior inside your always block, anything that changes in your always block has to be in your sensitivity list. So in your always block, you have the assignment of A, B, C, and D. So you have your sensitivity list should have A, B, C, and D. If you don't want to forget that, you can use the asterisk. And asterisk, it means everything in this block that is assigned to, you are sensitive to. Okay? Any question? Okay. So let's do a very fast example on this. So this one was from your lecture. It wants to compute the prime number from 4 bits. Remember? So you have the 1, 3, 5, 7, 13, and 11 are all primes in the 4 bits. Okay? And you created your Karnaugh map. You had your design, right? And you put a sum of product or products of sum. That's what you had in the lecture, okay? So you explicitly put the ands and the ors and the invert, okay? Now you're going to see the beauty of HDL. You don't have to explicitly put how it is designed. No, you are going to say, what do you need? And that you leave this implementation to the tool, okay? So this is the 4-bit prime. It's the same, like we said. We have module, you name it prime, and you end it with end module. You define your input, and you define your output. Input in, and output is prime, okay? Then inside the always block, you put, see, look at the always block. Always block is sensitive over the value of in. Whenever the input changes, the 4-bit value, whenever it changes, I'm going to check whether it's prime or not. So you have what? Case in. Case is a keyword. If you are not very familiar with programming language, case is used to check the value between its brackets and check whether it's 1, 2, 3, 5, 7, 11, or 13, or anything else. Okay? It's look at it as if it's like if else. Okay? Case is another way of writing the if else. Anyone doesn't know what is a case is? Okay. So you say case. If the input has a value 1, 2, 3, 5, 7, 11, 13, then I say is prime the output equals to 1. Other than that, the default, the output is 0. Did we put any description of the gates here? We didn't. We just wrote what? We just wrote what we want. We didn't put the sum product, we didn't put the product sum, no. We wrote what we want. And leave the implementation or the design to the tool. Doing this is just finishing the 4-bit prime number. Okay? This is another way of doing it, but I'm going to skip it. Now let's write any question on how we implemented the is prime. Now the test bench. The test bench, remember, we have the stimulus and we have the response. So again, we have the initial begin. At the beginning, I'm putting input equals 0, and you have a keyword called repeat. Repeat 16 times. That you have input equal input plus 1. So 16 times you are inputting plus 1. 1, 2, 3, 4. You are examining all the values of the input. And you are just calling prime, P0. P0 is an instance of the prime. Okay, and you are putting in and is prime. And you display. Display is just like monitor. Okay, it's the same keyword. So display the value of the input and the value of the output is prime. Okay, and you are seeing it. Does it match what you want or not? And you can see the results on the screen. Okay, when input is equal 0, is prime is 0. When input is 1, is prime is 1. And it matches what you want. Okay? Now, what is the take from all what I have been saying is that don't try to do the logic yourself. Okay? No. Think what you want write it and leave the logic to the tool. It will implement it. Okay? Write what you want, not how it's being done. Okay? Now the last part is how you are going to describe the FSM in Verilog. So what we have been talking about so far is combinational, right? You have output that will change whenever the input is going to change. Combinational logic. Now you want to do a FSM, synchronous sequential circuit. Synchronous sequential circuit is being implemented by RTL, like I said at the beginning of the lecture. Register, transfer, level. You define your combinational logic, you define your register, and whenever you are changing the output or the next state, you are saving it in a register, like the FSM, like the designing of the FSM. That's actually what we are going to do. That you are going to explicitly define the D flip-flop. This is the register. This is the state. This is what's going to save the state. And you are going to define the next state and the output as combinational logic. Okay? And let's see. So I am having an example from the lecture, the one that has the traffic lights. You have I don't know if you remember this example or not, but you have this state machine, and you have how the lights on the cross section is going to change based on the position of the car. So if you have the car at the east-west, the lights is going to change from green to yellow, and so on. Okay, so this was an example in the lecture, and if reset happens, you go to the initial state. Okay, so if not reset, you are going to your state. Else, if it is reset, you go into the initial state. Okay, and the output, if you remember, was having 6 bits. Okay, the changes of the lights. So we want to implement this using Verilog. Now, don't be scared when looking at this. Okay, so this is the Verilog description of the FSM. Now, if you look at this block, okay, at the beginning, you define the state value, like what you did exactly in the homeworks. Okay, you say that S1, I'm going to encode it to 001. S2, I'm going to encode it to 0010. Okay, are you going to encode your state as one hot, or you're going to encode your state as binary or whatever? Okay, so this is exactly the first block. You have how many states? 1, 2, 3, 4. You have 4 states. And you encode it, I remember in the lecture, it say encode the states using one hot encoder. Okay, so I'm giving the states one hot encoding. So there is a keyword in Verilog to define constants, or to define values that you want it to be constant through all your design. It's called define. Pick define. So I'm defining the state that's called G and S as 4-bit value, having the value 1000. You see what I'm saying? Everyone seeing what I'm saying? Okay, so you define the encoding of your states, okay? And also you define the encoding of your outputs. You have 1, 2, 3, 4, you have 4 outputs, and they have these values, okay? So at the beginning, you define the encoding of the states, like you're answering the homework. It's exactly the same, okay? And then explicitly, you define the DFF, which is what? The sequential part of your program. So remember, FSM has sequential part and the combinational part, right? The combinational part is to define the next state and to define the output. Okay, the sequential part is to define what? The register. So you define the register explicitly. You say that I'm having a module called DFF. DFF is your choice. It's arbitrary. It's not a keyword in Verilog. Okay, and you say it's define input clock, input in, and output called out. And always add positive edge of the clock. So positive edge is a keyword in Verilog. Whenever the value of the clock change at positive edge, input will go to the output. Does this match the description of D flip-flop? Right? At positive edge, the output will have the values of the input. This is what the always block means. Okay? So here you define the DFF. You define your sequential part explicitly. And then you have another always block that defines your combinational part. This is best practice, okay? You can define both of them in the same always block, but it's always combinational part by itself. Okay? Let's look at the combinational part. Again, so you have what? You have always the state and the value of the car is what? These were inputs to your state machine. And you put your what you want to implement. Okay, so you say what? If the state was at G and S, look at the figure at the top. If the state was at G and S, then your next state and your output line will have the value what? Remember this line that you took in the lecture, that if car EW, east-west, is true, then next one will take the value Y and S. Look at the figure. If car EW, the next state will be Y and S. You see it? Okay? And your output will be G and SL. Look at the definition. G and SL was 1, 0, 0, 1, 0, 0, 0, 1. Okay? Do you understand this line? Is it clear? And you define all the states like this. You define the next state and you define the output. Okay? So just to have like a beautiful syntax, sometimes you concatenate them together. Okay, but you can have them on different lines. So you see the curly brackets. You say I'm defining next one and I'm defining lights in the same line, but you can put it in two different lines. Okay? And then you have another one. Also, it's best practice to define the reset in a separate line. Meaning that, remember, all the always blocks are running in parallel. All of them are running in parallel. So the DFF, the module that's always a positive block, is always running. The combinational logic is always running. So you have to make sure whenever reset happens, it makes what? It interrupts both modules. So you have it outside your always block of the combinational logic. Make sure that the reset signal is outside your combinational logic. So you make sure that actually it's always running as well. So you make assign next equal, if reset is 2, it's going to GNS, the initial state. Else, it's going to your next state, who's called next one. Okay? I know it's a big code, but I just want to make sure to highlight that you have to define the combination logic alone, the DFF alone, the reset signal alone. Okay? And if you have any question on this, you can, of course, come to me. Just look at it again and ask me if you have any question. Okay? So I have 5 minutes left. Someone raised his hands. Any question? Okay. So there is a tool called EDA Playground, and it is actually cloud-based. So you just need an Explorer. You just need internet connection. Okay? And you write your Verilog, you write your test bench, and you simulate it, and you see the results. Okay, it's a very, very nice tool. You don't have to download anything for it, and it's you will use it, okay, to make sure that your design works correctly. It's called EDA Playground. So later on, go to EDA Playground, make an account. You will see that there are 2 windows. One of them, you put your design, your Verilog code, and you put your test bench, and you will see the compilation and simulation results in it. And actually, it can make synthesis as well. It can generate the gates that can be used to be downloaded on the FPGA. Okay? So, most importantly, you have to think before you code. Remember our flow chart? You have to analyze, you have to partition things before you code. Okay? Now, these are all my references. So there is a very nice training called Doulis. Actually, EDA Playground is based on Doulis, and the lectures, of course. And this is the end, but I want to, this is your laptop. I want to show them the EDA Playground, how it works.
So you want to just log in? Or you want to use your own?
That's okay. Maybe later after Paul, I will try to set it up. I want to show them how the EDA Playground works. Okay.